Welcome to the next lesson, which gives an overview of how concurrent programs are developed in Java. In this part of the lesson, you'll learn how Java supports the concurrent programming concepts that we covered in the first part of the lesson. Please note that Java threads are undergoing significant changes as part of Project Loom, which will be available in several Java releases from now and will radically overhaul the way in which threading is implemented in Java. We'll focus primarily here on traditional Java threads, but I'll also mention some of the changes that will be occurring as part of Project Loom. A Java thread is an object. And of course, what that means is it contains methods and fields. Historically, each Java thread has its own unique ID, its own unique name, priority, runtime stack, thread local storage, instruction pointer, and other registers that are used to implement it, both at the Java execution environment level as well as down in the operating system kernel. Traditional Java threads are now called platform threads in Project Loom, whereas the new so-called virtual threads are lightweight concurrency objects. And we'll talk a little bit now about how those compare and contrast. You can take a look at the link at the bottom of the slide to learn more about the difference between platform threads and virtual threads. And we'll cover these in more detail as we get further along. A Java thread can also be in one of various states. Here are some examples of the states that a classic Java thread or a so-called platform thread can be in. When you create the thread, it's in the new state. Once you go ahead and start it, it transitions to the runnable state. At some point, the thread scheduler and the operating system and the virtual machine decide to run the thread, in which case it's running. Once the thread is running, it can block, it can do timed wait operations, it can wait, it can terminate, and so on and so forth. And we'll cover all of these different states later when we get into the details of Java threads. There's also a number of states that a Java virtual thread can be in. I'm not going to cover them in detail here. You can take a look at the link at the bottom of the slide for a video that walks through this in more detail. A lot of this stuff is changing, so I don't want to get too wedded to the implementation details of a current snapshot of Project Loom in Java virtual threads. As we discussed in the previous video, Java threads can interact via shared objects, also known as synchronizers, and/or by using message passing. Shared objects are used to synchronize concurrent operations on objects to ensure certain properties are held or certain properties are obeyed. So here's a good example. You might have something called a critical section, which is a piece of code that needs to be protected from simultaneous read-write access or write-write access from multiple threads. The typical way of doing this in Java is by using some kind of mutual exclusion mechanism, which ensures that interactions between multiple threads won't corrupt shared mutable data. Mutable data is just data that could be changed. In other words, written to as well as read from by some other threads. The other form of control that's provided by shared objects is something called coordination. And these are mechanisms that are used to ensure that operations occur in the right order, at the right time, and under the right conditions. And again, we will come back and talk a lot about these when we talk about specifics of Java synchronizers. Speaking of which, there's a number of different Java synchronizers, quite a number, in fact, probably about a dozen or so, but here's a general overview of them. There are things like synchronized methods and synchronized statements, which kind of come from the early forms of Java where they had the synchronized keyword. There's also later mechanisms that came along in subsequent versions of Java for things like reentrant locks, atomic operations, which allow operations that work on variables to change its state atomically using compare and swap operations that are implemented efficiently by the underlying execution environment and the hardware, semaphores, condition objects, barriers, and so on and so forth. We'll spend a lot of time talking about these synchronizers, but I'm just giving you a quick high-level overview. This is what is typically part of what's termed the shared object mechanisms or the synchronizer mechanisms in Java. There are also, of course, message passing mechanisms as well. And these are used to allow messages to be sent from producer threads, one or more, to consumer threads, one or more, via some type of thread-safe queue. In other words, a queue that's synchronized so that it won't have race conditions when one thread tries to add an element or send a message to it, and the other thread tries to remove an element or take a message from it. So message passing is a very popular technique that's used when you don't want to be directly sharing state between these interacting threads. There's a whole bunch of thread-safe queues and thread-safe message passing mechanisms that are built into Java, including array blocking queues and linked blocking queues, priority blocking queues, synchronous queues, and concurrent linked queues. And we'll talk quite a bit about some of these mechanisms later on in other lessons that will be coming down the pike. I'd be remiss if I talked about how to do concurrency in Java without talking about some of the concurrency programming hazards that can arise. So Java shared objects and message passing mechanisms are explicitly designed to share resources safely, often efficiently as well, and to try to avoid various types of concurrency hazards. So one classic type of concurrency hazard that we've talked quite a bit about up to this point are race conditions, which can occur when a program depends upon the sequence or the timing of its threads in order for it to operate properly. If you want to see an example of a program that intentionally incurs race conditions, take a look at the link at the bottom of the slide. This is a test program that intentionally incurs race conditions because it doesn't have any synchronization between producer and consumer threads that are accessing a bounded queue. And of course, chaos and insanity will break out if you don't properly synchronize things. So this is just here to show you what not to do. Another common concurrency hazard you can run into when you're doing concurrent programming in Java are things known as memory inconsistencies. And these types of errors occur when different threads have inconsistent views of what should be the same data. This typically arises due to the way that modern multi-core processors do aggressive caching. And unless you do something to the contrary, like use a synchronizer, these caches aren't flushed. And therefore, you can end up with inconsistent views of memory that should be seen in a common, consistent way. Here's a simple example. This is a class called loop may never end. It has a Boolean field called mdone, which doesn't have any type of synchronization on it, just a good old Boolean field. And then we've got two methods. We have a method called work and a method called stop work. And what's happening here is that the work method, which let's assume it's in thread T2, the second thread, it's going to keep looping while the mdone field is set to false. So as long as it isn't done, it'll keep looping. Stop work, as you can see, is going to set mdone to true. And that will be called by thread T1 at some point. The problem here is because mdone isn't synchronized in any way, shape, or form, that thread T2 may never stop doing work, even after thread T1 sets mdone to true. And that may seem a little bit surprising at first, but that's really at the essence of memory inconsistencies. And we'll talk a lot more about that later. Yet another type of concurrency hazard that can arise in modern multi-threaded Java programs is something called deadlock, which can occur when two or more competing threads are waiting for the other threads to finish, and thus none ever do. This is sometimes called the deadly embrace or the circular embrace. And you can take a look at this example here. What we see here is that thread T1 owns lock L1 and wants to acquire or needs to acquire lock L2. In contrast, thread T2 simultaneously owns lock L2, but needs to acquire lock L1. And as long as they're stubborn and don't release their resources in any way, shape, or form, these two threads will be locked in a deadly embrace or deadlocked and won't be able to proceed. And we'll talk more about deadlock, and I'll show you some examples. You can take a look at an example here in my GitHub repository that demonstrates how deadlock can occur. So that's the end of our overview of how concurrent programs are developed in Java. Needless to say, we will cover this topic in much, much greater detail throughout the rest of the course. So I was just giving you kind of a preview of coming attractions to help you understand what some of the mechanisms are for threading, as well as some of the mechanisms for synchronization.